Right, so shall I continue? Right. So open question. So there was one open question that already been raised. So it's very tantalizing. That's so-called conjecture. So seems to be out of reach as of yet. So then I'd like to talk about some sort of pipe dreams. So far, the philosophy, sort of the of this approach was that we have some simple point, right? Some base point around which we can compute things like the matrix of all ones and things like that. So there is a simple point. Right. Second, there is a point that we really want to get to, 1. And so far, we said that as long as we have what I call a sleeve, a zero-free sleeve, we are fine. And 2 remarks here that that's the philosophy, but the practice of it whenever we had a sleeve, it always went through the real axis. Therefore, it was related to Lee-Yang phase transition. So things go badly if complex zeros end up too close to the real axis, right? And we relate complexity to the phase transition. But in principle, we can go up there. So the zeros may be just evil zeros, may be just lurking everywhere on the real axis. But we still can go around them, right? Just by, in physics terms, that would mean that we use complex temperatures, right? That will cool down or heat the system, go into complex temperatures. So, and that would imply that this notion of phase transition is really very loosely connected to computational complexity. But so the question that I'd like to ask is, are there any natural, quote unquote, examples of problems like this? So it sort of comes close, but I don't think quite makes it. This example of Eldar and Mehrban of complex Gaussian matrix with unit variance and vanishing expectation, vanishing very slowly, like 1 over log log. But is there like a combinatorial example where you say that there's a lot of phase transition going on in Lee-Yang sense, meaning that the zeros approach the real axis or even sit there, right? But we don't care. We kind of can go over or under. Yeah, so I don't have any.
Are there problems where we have good data on the closure of the set of all possible zero locations?
Right, so that's another point that I'm going to mention, but right, in a few seconds, right? So what I'd like to say that C is just a natural example of combinatorial problem where the Lee-Young is just all over the place. Phase transition, it boils, it solidifies, it melts, but we don't care because we go around it. So far we didn't have this example. So far, if we could interpolate, it was always sort of around the.
So what is the situation with the ferromagnetic Ising model? Because there are zeros approaching lambda is equal 1, right?
Yes. Right, so.
If you do a transformation to go from a different perspective, there's still this randomized, this Glauber dynamic.
Yeah, right, but that's the question is what do you do here? Like,
so if you stay in the original model, what do you?
Then stay in the original model. So the original Lee-Young says that there is no phase transition, right, at any temperature other than 0, right? If you have non-zero magnetic field. Right? So, so it's still very physical, right? So what I want to see if you come up with like complex temperatures that you cooling things or heating things, but going into a complex plane.
What if you want to do like a matching polynomial at a big negative number?
Yeah, I thought about it. That would be a good thing. But for that you will need a bound for the roots, not only like Hellman-Lieb, but also on the other side. Do we have? Yeah. Then we can go get. Yeah. Do we have an example of it? Yeah. But that would have been an example. Yeah.
I think for large graphs, the zeros become dense in that interval. I mean, of the.
Yeah. So that brings up the next topic. So that's even more kind of dreamy than this one. So far that was the idea, and here's the some hand waving. So what if we just it suffices to not to have zeros just around the starting point and around the end point. So it suffices not to have zeros around 0 and 1. So these evil zeros may surround 0 so that we cannot really through a sufficiently wide sleeve. But what we say, we introduce some dummy variable, go high dimension, and jump over this fence of zeros. And in principle, that can always be done. That Mark Rudelson convinced me. It's a very simple argument, only that you don't know how to do it effectively, right? So you introduce new variable that's responsible for moving the zeros away, if you know where they are, right? So what you do, so you move the upper half up, you move the lower one down, you do interpolation, then you pull them back in. So you interpolate it. Can it be done efficiently in any interesting case? So the reason it's sort of maybe not so outlandish there it sounds, that in all examples of hardness that we have so far, we do have zeros dense around the endpoints. I think that's, I can say without the fear of contradiction, that we don't really have this. What happens in the hard problems in that zeros actually bog us around the point that we want to arrive to. So therefore, if we had an example like this, that maybe, just maybe, we don't need a connected sleeve, that we can always lift it up. Well, in theory, yes. So that's exactly as I said. So move upper ones up, lower ones down, interpolate, close them back so that you interpolate the same thing, right? So again, so this is no idea, right? So But it's a bit suspicious that in all hardness examples, we do have zeros kind of dense around the endpoint. So finally, I'd like to go back to the question that Alistair brought up yesterday. So relation between correlation, decay, interpolation, Markov chains. So the relation between interpolation and correlation decay, physicists looked at, right? So certainly, so sometimes Lee-Yang phase transition is equivalent to non-uniqueness of the Gibbs measure. Sometimes they're not, but so that's sort of certainly people looked at. Relation with Markov chains not so much. And as I walked here yesterday from the hotel, had an idea that I'd like to share with you. But since this idea is 1 day old, and we know that 1 day old ideas rarely see 1 week anniversary, right? Let alone 1 month or 1 year. So it may be a pretty bad idea, but it's still, I like to talk about it, right? Because it's been the 2nd day, I still find it's okay. So what are we after? So suppose that we have this family, combinatorial family of subsets that we started with, right? And we want we define the partition function. That's the sum over all sets in the family, and then the product over elements of the set of the variables z sub I. So suppose that we know the easy point, the reference point is 1, the point of all ones, just like we had for the permanent for the graph homomorphism. So suppose we want to prove that this function is not 0 provided this z is in the polydisk, so close enough to 1. And we want to prove it using Markov chains. So that will be our connection. So suppose, so what do we say? So we say that, suppose that there is a Markov chain on this family, which makes local moves if S goes to S prime, then they don't really differ that much. Something like that, that you just replace one element. And that the matrix of the steady state is uniform, right? And the matrix is symmetric we have some control over the spectral gap. So spectral gap, I don't know, 8. Something like that. Right, so I want to prove that in this situation, there are no zeros in the polydisk. How would I prove it? I would say something like this. I would say that suppose that the partition function indeed turns into 0 in this polydisk. What does that mean? That means that if I consider the vector of all ones parameterized by subsets in the family, then it will be orthogonal, well, the scalar product will be 0 with this vector of monomials. That's exactly what it says, right? So that the partition function is 0. So because this scalar product is the partition function, right? So what does that mean? That means that the vector consisting of this, consisting of these monomials is in the eigenspace of the smaller eigenvalues. Well, that's probably what I'm saying is gibberish, but you know what I mean. So it's orthogonal to the largest eigenvalues, eigenvector. So therefore, the matrix A, the matrix, let's call it A. The matrix A is a contraction. So A is a contraction with a factor like eta on this vector of monomials. But the point is that if the moves are local, it cannot be a contraction, right? Because what it does, so if I multiply it by this vector of monomials, what it does, it replaces it with a vector, some convex combination of monomials that are utilize pretty much the same variable, maybe one or two different. Right. And if so, if you have that condition that it's close to 1, then you guarantee that it doesn't contract much, right? Because you just replace one or two variables that are close to 1 by another that is close to 1. You don't replace all n, right? Or so, and that shows that it really cannot be. A bad contraction. And the contradiction purportedly shows that there are no zeros in the polydisk. It would be nice to have examples if it's not a complete nonsense. I mean, it seems to hold water after one day. No examples, but so yeah. And that's pretty much. I'm out of time, right? Or anyhow, I'd like to be. So, so that's then the end of it.
So we needed 2.